Hello, everyone. This is Jeremy, and I will be presenting the last slideshow for our research project with myself and Jacob. And it is on energy profiling of neural network quantization schemes for GPUs. I'll briefly introduce the idea. I'll talk about the quantization schemes that we've analyzed in this experiment, and then I'll discuss the experimental setup that we worked with, and then move on to an evaluation section and conclude with our findings. Well, central to the recent explosion in deep learning research has been the computational acceleration provided by GPUs on neural networks. A high-level perspective of deep neural networks is that a DNN is simply a sequence of matrix-matrix multiplication sandwiched between inexpensive nonlinearity layers. Training these deep neural networks, however, remains a bottleneck in research and industrial applications. Work in the last decade has demonstrated that deep neural network computations can be performed with single precision data types at minimal loss of accuracy while doubling performance through reduced memory usage and decreased memory transfers. Performing these computations on lower bit data types has the immediate effect of reducing memory footprint. And more recently, work has explored the lower bounds of the performance accuracy trade-off with data types at and below the byte level. However, in the race toward the bottom, an important consideration has been neglected, and that is power consumption. A key benefit of low precision training and inference of deep neural networks is the expected decrease in power demand. Since the prevalence of deep neural network technologies in embedded systems like self-driving cars and smartphones, where power consumption is an important consideration, it's anticipated to grow rapidly in the coming years, it's essential that the effects of low precision training are analyzed. During our review, we found that nowhere in the literature on low-bit deep neural network training is energy consumption addressed adequately. We found that energy benchmarking is only done for matrix multiplications and other small kernels, but not in the wild. Nobody is doing it for actual implementations. While these results demonstrate that the reduction in energy costs that is possible by performing computations with lower precision data types, they are not indicative of actual usage, since much of the deep learning today is done at the high level in optimized libraries. This is of great practical importance in an industrial setting. For example, major cloud services like Apache Spark that have tens of thousands of servers could reap considerable savings with battery-ready deep neural network implementations that perform operations on low bit width data types that have an affordable loss of precision. In this work in particular, we will evaluate the energy costs of several low-bit precision schemes on AlexNet, which is a deep neural network, using the ImageNet, Cipher10, and MNIST datasets. And the deep neural network topologies considered are configured for binary and ternary precisions, and I'll go into that in a little bit. But in general, we have adapted some TensorFlow code from repositories, and we benchmarked each of these using the NVIDIA profiler that's native on the Pascal GPUs that we have access to. And in this project, we basically aim to discover the magnitude of the savings that these quantization schemes yield and where the greatest gains come from. Furthermore, we evaluate the relative strengths and weaknesses of these different quantization schemes. So the first scheme that we examined is called the binary net scheme. In this work, they've applied quantization on a matrix, multiply, accumulate operations to compare the effects of single and double floating point and custom half precision fixed point data type. They only found a marginal increase in the test error as the bit precision decreased, which is actually pretty solid. Another work that we're comparing is the binary weight network. In this network, the convolutional operator is approximated with a binary filter, and multiplication is then binarized to just simply addition and subtraction, which yields considerable performance improvement. And the trained binarized weights are trained in both the forward and backward passes. And this whole network results in a very drastic speed up and actually some slight improvement over the baseline accuracy. Additionally, we'll consider the XOR-net deep neural network, which extends the previous network to include binarized inputs. This requires binarized inner products as well, so there's an additional level of computational complexity that goes in and the ability for significant loss. So as a result, there's a 58 time speed up, which is quite excessive, but there is a very large loss of accuracy over the baseline. Furthermore, we'll also consider a trained ternary quantization. This is a quantization scheme in which values can take either -1, +1, or 0. They also refer to it as sparse binary weight networks. And it actually outperforms the original full precision AlexNet network by 0.3%. And last, we will consider the Do-Re-Fa net, which is a binary training of all weights, activations, and gradients. And they've figured out how to handle that in both the forward and backward passes, which must be done deterministically for the weights and activations, but stochastically for the gradients. And that has to do with the gradient not being well defined in the backward pass when chosen from a specific sampling distribution. And it actually has pretty good geometric mean test accuracy. So in our experimental setup, we used an NVIDIA GTX 1080 Ti on BG9. We used code implementations available in TensorPack, which is a suite of high-level training APIs built on top of TensorFlow. One main criticism of TensorFlow is that the code is written for readability and not necessarily for efficiency. TensorFlow forces a programmer to basically be concerned with details unrelated to their problem, and that typically introduces further inefficiencies. But TensorPack is designed to avoid this. In essence, TensorPack is a collection of highly efficient, lower-level TensorFlow subroutines constructed to maintain high performance while simplifying programming by, in fact, hiding the performance details. We used AlexNet network architecture, which is a recent deep learning model designed for large-scale image classification. Originally, AlexNet was used to achieve state-of-the-art success with accurate prediction on the ImageNet database, which I'll talk about in just a moment. And we compared each of the quantization schemes on 3 image classification datasets: ImageNet, Cipher10, and IMNIST. ImageNet is a database of images corresponding to the WordNet database. It contains over 15 million images with 22,000 categories, and it's used in lots of large-scale competitions. Cipher10 is a dataset with 60,000 labeled color images in 10 different classes, and the IMNIST dataset is basically the classical image recognition data set. It's got 70,000 grayscale images of handwritten digits 0 to 9, 60,000 images for training, and 10,000 for testing. In our evaluation, we compared multiple versions of these quantization schemes provided here. The easiest description is given by the triplet of weight, activation, and gradient, and the value inside of that ordered triplet refers to the bit width of the respective value. So in the full precision, everything is 32 bits. In the binary weight network, we have single bit weights, but 32-bit activation and gradients, and so on and so forth. So we've compared the full precision with the binary weight network, the binarized neural network, the trained ternary quantization, and then 2 settings for the Do-Re-Fa net. And we trained each of these networks until their validation accuracy ceased to increase. These are the best case performances for the 3 different data sets that we evaluated, and the development of the model error over the course of training is given in these 2 figures. So you can track the accuracy as the number of epochs increases for each of the quantization schemes that are under consideration. A couple things that we've noticed is that the Do-Re-Fan binarized neural networks perform significantly worse than the others. The main difference here between these 2 sets of networks is that the Do-Re-Fa network has low precision activations while the binarized neural network doesn't. Basically, we feel that this constraint is just it's too strong, and it causes information loss in the network and significantly harms the progress of the learning procedure. We also see that changing weight precision has little to no effect on accuracy of the network. This is, in theory, a great win for performance. Indeed, reducing the size of the network weights promises to be more fruitful in terms of performance and energy gains, since these low precision weights do not harm network performance. We really only have gains. On the other hand, this is not really the case for low precision activations. As you can see in the binary neural network model, it maxes out its performance on the Cypher 10 dataset at about 40% accuracy after 60 epochs of training. The full precision baseline reaches this level of accuracy after only 10 epochs. For the energy savings to be profitable, it would have to be able to compete with to complete an epoch with a power consumption at like 1/6 of the baseline. That's just not realistic at this point. So we decided to put these theoretical notions to the test and use the NVIDIA profiler to calculate the average power consumption of training each of these models. Each network requires roughly the same training time, and we can see a couple of clear trends. The full precision network here requires relatively little energy, and the ternary network requires a lot. The other network architectures battle around middle. But this isn't really what we expect. Looking at the source code, we find that all the arithmetic is ultimately done in 32-bit arithmetic storage. We don't expect to see a decrease in energy consumption due to small data types being computed at the ALU. However, we would expect to see some energy savings due to the decreased memory traffic required to pass the network weights and activations between the device and the host. Nevertheless, we observe that this effect is negligible. In fact, the cost of casting between different data types can add significant energy expenses to the training process. It's confirmed by the NVIDIA profiler that many of these applications spend an overwhelming amount of time with their execution in the casting kernel. We use the DeepBench benchmarking tool to measure latencies and energy costs on native hardware. And we ran a set of matrix multiply and convolution benchmarks on the GPU at 3 different precision levels. And we did this because we see that hardware support for these lower precision data types is absolutely necessary. And if we want to see any performance gains from these quantization models, then we really need to understand what the baseline is. So again, we benchmarked at 3 different levels: 8-bit, half precision, and single precision float. And we used the profiler to measure the energy consumption during the execution. You can see the table on the bottom relates the average energy consumption of each of the benchmarks. And the pattern we see is what we would expect. The larger the data type, the more energy is consumed. The savings are minor, but not insignificant. There is one caveat that the benchmarks for the half precision floats took almost 10 times as long to execute as for the other 2 data types. This means that any savings gleaned from using a smaller data type is negated by the extended execution time. So to figure out why this is, we look at the manufacturer's specifications for our GPU model. Of particular interest is the maximum flop rate for each of the supported floating point data types. For single precision floats, the rate is 377 gigaflops per second. For single precision, it's 12 teraflops per second, and for half precision, it's 96 gigaflops. So using 16-bit floats, one must sacrifice 2 orders of magnitude in floating point performance. Furthermore, even as arithmetic on 64-bit floats is 4 times faster than the 16-bit. So if we really want to reduce energy consumption and training time via low-level quantization, then we absolutely must cater the hardware toward that end. Some steps toward this have already been taken. For example, starting with the Volta, NVIDIA has extended support for low-precision schemes at and below the 8-bit level. Furthermore, neural network training schemes that use several different levels of precision are offered currently in recent versions of cuDNN on this same Pascal architecture. But in conclusion, we've covered the mechanisms of neural network quantization and their implementation in contemporary machine learning libraries, and we profiled we profiled energy consumption and found that within these high-level libraries, there were not optimizations in place to allow these schemes tenable or useful for real-world usage. We looked more deeply into this area by benchmarking the existing low-precision support for Pascal GPUs, and we found that the half-precision float had less than satisfactory throughput when compared to high-precision data types, and it's not advisable for usage. In summary, we found that while quantization schemes offer much promise in the way of performance, with negligible losses in accuracy, there's still a lot of work that needs to be done to make these methods profitable. We just think that hardware manufacturers need to take more care in optimizing for these methods and indeed help the burgeoning field of deep learning. And we anticipate that that will be seen in the near future. Anyway, thank you very much for your time. I hope you enjoy watching this video, and it's been a really nice semester.